In this video, we're going to look at the cross product and the dot product of vectors. So we'll start with the dot product. And it's best just to do this by example. So let's say you have, say, two vectors, say, call them V and W. Find the dot product. And usually put a dot between the two that kind of indicates you're going to do the dot product. And it's very simple to do this. What it is when you do the dot product, let me show all the steps here. And what it is, you'll multiply the corresponding components and then sum them up. So in other words, you'll have 3 times minus 1 plus minus 2 times 5. This is equal minus 3 minus 10 minus 13. So you simply multiply the corresponding components. 3 times minus 1 minus 2 times 5 and add them up, get minus 13. Now, the dot product may be used on any dimension of matrix of vectors as long as they're the same dimension. So it could be 3-dimensional vectors, 4-dimensional vectors, etc. And let's do a 2-dimensional. Once again, remember, we have different notation for vectors. Sometimes vectors might be represented, with the IJK notation. So we might have a couple of vectors, maybe like this. Let's say you have W is 4I minus 7J plus 3K. And let me call a vector, let me just call it Q just to do something different. And then maybe Q is minus 1I plus 2J minus 3K, like this. And so we're going to find the dot product. Find W dot Q. Now, I sort of prefer the angle bracket notation. It's up to you whichever one you like best. You can use that one. And so if we do this, so I'm going to change these to the angle brackets. So remember, this is the same as 4 minus 7, 3. And we're going to dot this with minus 1, 2, minus 3 like this. Once again, multiply corresponding components. So we'll have 4 times -1 plus -7 times 2 plus 3 times -3 like this. And that's going to give us -4. What, -14 -9. Let's see, what's that? -23 -27 if I did my arithmetic properly. So notice for the dot product, we input 2 vectors. And the output is a scalar, a number. And something very interesting is that if the dot product of 2 vectors equals 0, then the 2 vectors are perpendicular. In fact, you can actually say as an if and only if. Suppose V and W are 2 vectors of the same dimension. Then V and W are perpendicular. If and only if their dot product is 0. V and W are 2 vectors of the same dimension. Then V and W are perpendicular if and only if the dot product is 0. So we saw in the last 2 examples, the dot product of these 2 vectors not 0, so they're not perpendicular. Dot product of these vectors not 0, so they're not perpendicular. And so let me make up a one where they are. So let's say, suppose, let me call this one U this time. U equals 3I plus 4J minus 2K, and V, let me make V in the angle bracket notation. So let's say that this is going to be 2, 1, and let's say that this is 5. And find U dot V And let's go ahead and do that. Now you don't have to write out all the details every time like I'm doing. I'm just doing this to be sure that everyone understands. So let's do this once again. Do the normal. 3 times 2 is 6. 4 times 1 is 4. Negative 2 times 5 is 10. Looks like that's 0. Since the dot product is 0, then in this case, U and V are perpendicular. Since the dot product is 0, U and V are perpendicular. Again, that's the way to check to see if two vectors are perpendicular. Take the dot product. And if it's 0, they're perpendicular. If it's not 0, it's not perpendicular. And this will work for any dimension vectors. Again, the two vectors when you do the dot product must be the same dimension. They either have to be both 2-dimensional, both 3-dimensional, both 4-dimensional. But again, if you take their dot product and it's 0, the two vectors will be perpendicular. One final thing to note that if two vectors are the same dimension, once again, let's say, suppose, once again, let me call, say, V and W, just sort of a general case, are vectors the same dimension. Then if we do V dot W, that's going to be the same as W dot V. Because all we're doing, if you look back, say, at one of our earlier examples here, we're taking corresponding components and multiply them. So if you take 4 times -1, it's going to be the same as -1 times 4. So if we flip these two, each of these products would be the same. Excuse me, V dot W is the same as W dot V. Next thing we want to look at is the cross product. Now, the cross product may be applied to 2 3-dimensional vectors only. Can't be applied to 2-dimensional vectors or 4-dimensional vectors. It has to be 2 3-dimensional vectors. And once again, the cross product is best demonstrated by some examples. So once again, let me just call this, say, U is 3 minus 1, 4. And let's say V is 2, 5, 1. Find the cross product of u cross v, like this. And the way the cross product works, it's written like this. And what you do, you set up your I, J, K, and then put the first vector in the second row. And put the second vector in the third row. And find the determinant. Remember, this is the symbol for the determinant. And let me write this out. Now, this is a case where if you're doing a 3x3, it's better to do it the standard way than the quick way, because if you do it the standard way, it'll keep the I, J, and K in the proper order, and it makes the cross product come out real nicely. So let me show you what I mean. So once again, as we did before, go across the first row and cover up the row and the column of that first entry. So we'll cover up that and then write down what's left. Again, I'm going across the top row. I started with this first element. I put it in front, cover up that column, that row, write down what's left. Then go over here and go to this next element here in the first row, which is J. And cover up the column that J is in and the row that J is in. And write down 3, 4, 2, 1. Finally, go to the last entry in the first row. Gives us K. And cover up that column and that row. Like that. And then again, remember when you're doing the determinant, we alternate the signs: positive, negative, positive. And of course, do this determinant here. And that's going to be I, upper left times lower right. Upper right times lower left. The next one's a minus J. Upper left times lower right. Minus upper right times lower left. And J. Upper left, lower right, minus upper right times lower left. If I can get it on the paper. So again, what do we have here? This is going to be -1, -20. So it looks like -21. I. This is going to be 3 minus 8. Looks like that's -5, but it's a negative of a -5. Like this. This is 15 minus a -2. That's going to make it a +2. So it looks like 17K, like this. Now, a very important property of the cross product is that it will produce a vector that is perpendicular to each of the vectors that were inputted. So let me write that down. The cross product will produce a vector that is perpendicular to each of the original vectors. So let's check to see if that's true. So again, our vector that we got here was this one. Remember, we can write this as minus 21, 5, 17, if you like the angle bracket notation. So again, let's test this. So let's check to see if we got a vector that's perpendicular to each of the original vectors. So let's test the vector we found, minus 21, 5, 17, and take the dot product. Remember, that's the way we check to see if something's perpendicular. We use the dot product. And if that's 0, then they are perpendicular. So 3 minus 1, 4. Does it really look like this is going to end up being 0? So let's take 3 times 21. What's that? Minus 63. 5 times minus 1 is minus 5. And 4 times 17, what's that? 68. And sure enough, this is negative 68, positive 68, so it's going to be 0. So that's perpendicular to one of our original vectors. So let's check the other one. See if it's perpendicular to the other vector we inputted. So 2 times 21, what's that? Negative 42. 5 times 5 is 25. 1 times 17 is 17. And so if we take 25 plus 17 is 42, minus 42, it's 0. So sure enough, that the vector produced by this cross product gave us a vector that was perpendicular to each of the original vectors. Now notice the other thing with the cross product, unlike the dot product, we inputted 2 3-dimensional vectors. Again, it only works with 3-dimensional vectors. We input 2 3-dimensional vectors. And the output is a vector. Remember, for the dot product, the output was a scalar. Here it's a vector. Like that. Something else really important, unlike the dot product, remember they said dot product said that, say, V dot W was the same as W dot V. Well, that's not true of the cross product. V cross W is actually equal to the negative of W cross V, like that. So you'll get a negative answer. So in other words, in this case here, if we had done V cross U, we would have gotten a vector 21, negative 5, negative 17. So the answer would take the negative of each of the elements. So we input 2 3D vectors, and the output is a vector. Now, this is not the easiest way to determine 2 vectors are parallel, but it is one way. So there's also a theorem that we have that says two three-dimensional vectors are parallel if and only if their cross product is 0. Remember, for the dot product, if the dot product two vectors 0, that means they were perpendicular. In the case of the cross product, if the cross product 0, then they're parallel. Now, there's an easier way to determine if two vectors are parallel. So note two vectors are parallel if and only if they are scalar multiples of each other. And that's by far the easier way to determine if two vectors are parallel. So, for example, the vectors, say, 3 minus 1, 5, and let's say 9. Let me make this a -9. -9, 3, and -15 are parallel because we can tell they're parallel because if you take the original one here, multiply by something, we can get this one. In fact, if you multiply this one by -3, you end up getting -9, 3, -15. So they are parallel.